Hello, my name is Luis Galvez, and during this presentation I'll be talking about the element distinctness problem. I'll talk about what it is, the solution, and we'll talk about the lower bounds and see a proof of why the current lower bound cannot be improved. So getting started, what is the element distinctness problem? So what it does is, it determines if all the elements in an array of length n are distinct or not. So we have an input, and this is an array of length n with elements, and the program is going to tell us whether it only has two outputs, so it's going to be yes or no, and it's going to output yes if all the elements are distinct and no if all the elements are not distinct. As an example, down below we have an array A, which consists of the numbers 2, 5, 1, and 4. And so the output is yes, because there are none of the elements in the array A are equal to each other, therefore all of them are distinct. And then we have an array B, which consists of numbers 3, 5, 4, 3, and it's going to output no, because, well, the first and the last number are equal, this one's being 3, so the program is simply going to output no. The solution for this, a trivial solution, is to sort all the elements and compare all the pairs of numbers adjacent to each other, right? So we take the array, we sort it, and then we go pair by pair comparing the numbers. And if at some point these two numbers are equal, then we output no. More formally, the solution that this problem uses is a decision tree model. We're going to go ahead and see a little bit more in detail how it comes into play, and then the time complexity for this special problem is big O of n log n, because sorting cannot be done any faster. So now that we talked about the solution, let's go ahead and talk about the tree model. So the tree model consists of a sequence of numbers, from x1 to all the way to xn, so x1, x2, x3, and let's assume that all these numbers have already been read. So the program that this decision tree model uses is a label tree, and the non-leaf node labels are labeled I:j or I to j, and then the leaf node labels are the value to be output. The operation that this tree implements are such as the ones that consist of less than or equal to, greater than equal to, is equal to, or is not equal to. And then it uses comparison which starts at the root, ultimately reaching a leaf to be output. And then each node labeled I to j, we're basically comparing the number positioned at I and the number positioned at j, and then we're going to go down the tree following the corresponding path. So as an example, we have this decision tree model, and it takes in the array of 7, 10, and 5. So let's go ahead and simulate what the tree would do in this with this specific array. So first of all, let's begin at the root. We have 1 to 2, so we're going to compare the numbers at the index 1 and the number at the index 2, and so therefore it is 7 and 10. We see that 7 is less than 10, so we're going to go ahead to the left, right, because 7 is less than 10. And now it's going to compare the numbers 2 to 3, so we see that 10 is greater than 5, therefore we're going to take a right. We're going to go down to 1 to 3, which is 7 and 5, and now we know 7 is greater than 5, therefore we take another right, and then we end up at a leaf node, which is 3, 1, 2, right? So we have this leaf node right here, and this is basically a permutation of the original array. So this was the input 7, 10, 5, and then the output is 5, 7, 10, because that was a permutation that we took by taking the left, right path. So the sorting lower bound for this problem, we're going to talk about it. we know that the input x is some array with elements from 1 to n, and then we know that the possible number of answers is n prime, which means every permutation of x, and then the program tree must have at least or more n prime amount of leaves. Therefore, the time complexity is equal to the height of the tree, which is log of n prime, which amounts to big omega of n log n. So the question here is, can we improve the time complexity for this problem to something faster? The answer is no, and we're gonna see why. And so this means that the lower bound for this problem is big omega of n log n. And so we are going to prove that there must be at least n factorial. I'm sorry if I said n prime before. I meant n factorial. N factorial leaves with n-dimensional geometry. So to prove this, we have to follow a series of steps. So this is the main claim, right? We're saying that the time complexity cannot be any lower than n log n, and therefore we're going to take a series of steps to determine why. So the first step is to interpret x as a main point in an n-dimensional space, and then we're going to restrict the instances to the unit n cube, where x of I falls between 0 and 1, including 0 and 1. We're also going to go ahead and expand on each and every single step so that we get a better understanding of what is going on. And we're also going to see visual representations of the steps. The second claim, we're going to say that the region R of L be instance for which a leaf L is reached on execution. So basically it's just saying we begin at the root, and eventually we're going to reach some leaf, and then that leaf is going to be an instance of the region, and we're going to say that this region is connected. The third claim is to let x be a sequence of numbers with distinct elements, and then y be a non-trivial permutation of x, where and then we're saying that x and y must reach distinct yes leaves. So we have two arrays. We have array x and we have array y. X is just some sequence of numbers, and then y is a variation, a permutation of x. And then lastly, we have the fourth claim, which is that the number of yes leaves is greater than m factorial, and this means that the time complexity cannot be improved. So let's go ahead and begin with the first step, which is to interpret x a point in n-dimensional space, and then we're going to restrict the instances to the unit n cube, where x of I falls between 0 and 1, including 0 and 1. So for example, we have this two-dimensional scenario, right? We have two x's. We have x2 going vertically, and then we have x1 going horizontally. And we see that if we take two values, for instance, let's take 0 and 1. So we have 0 and 1. That point would, imagine 1 is somewhere around here. That point would fall somewhere, or not somewhere. That point falls in the yes region. Therefore, the program would output yes, because the two numbers are distinct, right? 1 is different than 0. And so if we swap those elements, if we say 1 and 0, so imagine 1 is somewhere around here, we say 1 and 0, it would fall under the other yes region, because 1 is different than 0. However, if at any point, or if at any moment in time there's a point that falls between these diagonal, that means the two values are equal, like 1 1 or 2 2 or 3 3 4 4, so on. And so the only way the program would output no is whenever there is 2 points that fall under this diagonal. So that's how we represent an n-dimensional cube in 2 dimensions. We're also going to expand this in 3 dimensions later, but first let's talk about connectivity and why it's important. So we're going to move on to step number 2, and we're going to let the region R be instance for which a leaf L is reached on execution. So we're going to begin at the root, and then eventually we're going to end up at some leaf, and we're going to say that the region is connected. So what is a region that is connected? Well, we have 2 points, x and y, and then if we can make a path from x to y that is passing through R, through the region R, that means the region is connected. And then a special case of connectivity is convexity, which means that if we can draw a straight line between the 2 points inside the region, then the region is convex. So for instance, in the left picture, we have a circle, and then we have 2 points, and we can draw a straight line in between those 2 points. Therefore, the region is convex. So what we can say is that convexity means connectivity. However, if we look at the right picture, we have 2 points, x and y, and we see that the straight line that goes between the 2 points that connects them, there's a segment of the line that lies outside of R. Therefore, the region is not convex. So visualizing this in 3 dimensions, as we can see, we have 3 axes. We have x1 going horizontally, we have x2 going vertically, and then we have x3. x3 would be the same as going out and in of the screen, right? Because we are in 3 dimensions. So let's say at some point the tree made this comparison, which is that x3 is less than x1. So how would we visualize this? Well, we have the 3-dimensional cube, and we start by selecting the region or the plane where x3 is equal to x1, right? So it would basically be this plane that slices the cube into 2 parts. And so this means that if we wanted to take the portion where x3 is less than x1, we would take this slice right here. We would take the wedge shape area that is facing us. And then if we wanted to do the opposite, well, we would simply take the outer area, or the area that is away from us. And this would simply mean that each time we split this cube, we would keep convexity, because the main concept of the main concept of slicing the let's say our region is a set. If we keep on slicing the set, and we take one part of it, we're able to maintain the convexity of each region, right? Of each sub-region. So let's say we take this, or let's say we take the opposite area, and then we slice it again, and then we take the remaining, and then we slice it again. We can do that as many times as we want. No matter how many times we do it, we will be able to maintain convexity. And so, explaining it in a more formal way, we're going to say that we're going to take 2 arrays, x and y, and we're going to let them be 2 points in R. So we're going to follow a series of executions, and we're going to analyze them. So first, in the first execution, we have an instance that is equal to x, where L is reached. So in the first execution, we were able to reach a leaf. In the second execution, the same thing happened, right? Because it goes through the same process, and then we reach an L leaf. However, in the third execution, we have to define z. How are we going to define z? Well, we do this by let's go from the start. We have z, which is represented as a point, but in reality it's just a series of points, right? Because we have z of 1 all the way up to z of n. And the way we're going to represent z is we're gonna multiply z. So we're going to do p times x of I plus 1 minus p of y of I for all I. So and p has to lie between 0 and 1, including 0 and 1. So all we're doing here is we're making z fall in between between the straight line that is formed from x and y. So that's all we're doing here. We're just setting z so that it falls between x and y. That's why we're setting these boundaries, so that it never goes outside. So let's analyze this execution. So we would begin at the root, and then let's say that the less than path was taking, right? So let's say the less than was the path to the left, so therefore it would go to the left. And then after this execution, after this path was taking, the same thing would be done for the second execution, right? So we can say that for both executions of x and y, both less than paths were taking. And so for the third execution for z, all we're gonna do is we're gonna multiply each value from the right and left with the same value that we're assigning it in z. So for example, in the left side we have x of I, which is x of I. We're going to multiply it by p, right? Now we're going to take the left side of y, which is this one, and we're going to multiply it by y minus p. And we're going to do the same thing for the right one. So we have p, we have x of j, which belongs from this right side over here, and then we're going to add it to 1 minus pi times y of j, which comes from over here. And so this, we would end up with this inequality, and all this inequality means is that z of I is less than z of j. And what does this mean? This means that the same path that was taking in z of in this comparison was the same path that was taking in the first and second execution. So we can say that the less path was taking in execution 3. And so if we can apply this to z, we can apply it to any other path reaching L. And so we can say that the region R is convex. Now that we have been able to go over the second step, let's take a look at the third step, which is we're going to make a claim. And this claim is simply that we're going to let x be a sequence of numbers with distinct elements and y be a non-trivial permutation of x. And we say that x and y must reach distinct yes leaves. So we can assume by contradiction that if x and j reach the same leaf, we can also say that the region R is connected, right? Because we just proved it. Therefore, every path P from x to y has to pass through L. We just showed this in the previous slides, and we're gonna go more in depth on how this contradiction works out. And so we can say that there is a permutation Z in a path P where no leaf is reached, right? So there is a permutation within the array in the path, or that takes the path where no leaf is reached. So expanding on the proof by contradiction, we begin by defining a continuous function, which is f of w, and all it's going to do is going to take the distance or the difference between w of I minus w of j, where f of x is less than 0 and then f of y is greater than 0. So if we apply the mean value theorem, we can say that there is a path P where f of z equals to 0. But whenever f of z is equal to 0, this would mean that there are at least two values that are equal to each other in the array, right? Because z and I, when z and I is equal to z and j, then f of z would be equal to 0. And this means that the tree would be reaching a no leaf. But this is a contradiction. But so since we have arrived at this contradiction, we can say that x and y will reach distinct yes leaves. Now this contradiction works because we have made a subclaim which states that there exists an I and j such that x of I is less than x of j, while y of I is greater than y of j. So to better visualize this and understand what is going on, let's take two arrays. We have array x and we have an array y. And then we have a function b, and what b does, it's gonna sort the array. So for example, we're gonna take the array x and we're gonna put it through b, and so it's gonna sort the array in ascending order, which is gonna end up as 2. So first we have 5, 7, 3, and 2, and then it's gonna sort them, all the elements, and it's gonna end up as 2, 3, 5, and 7. And so this the result of b of x is a permutation of x, right? And so if we apply the same permutation that was done to x to y, we're gonna end up with a different permutation that is not sorted. So for example, in this case, the decision tree steps that were made was 4, 3, 1, and 2, because the fourth number goes first, and then the third number goes second, and then the first number goes third, and the second number goes last. So if we apply the same permutation to y, well, we would end up as 4, which is 2 to 2, right? So we have 2 and 2. Then we have 3. The third spot is 3 and 5, which is 3 and 5. And then we have the third number, which is we have the first number, which is 5 and 7. So we have 5 and 7. And then we have the second spot, which would be 7 and 3, and we have 7 and 3. But we can observe that b of y is not sorted. So whenever we apply the same permutation to y that we did to x, we can conclude that y cannot be sorted because there is a pair I of j such that I is less than j, while the numbers are in increasing order. Now that we have reached this conclusion, we can move on to the fourth step, which is a claim. This claim says that the number of yes leaves is greater than n factorial. And so we know that the number of distinct permutations that can be applied to any array is n factorial. Therefore, the number of yes leaves must be greater or equal to n prime. This means that the time complexity has to be bigger or equal to than the height of the tree, which is log of n factorial, which makes the lower bound big omega of n log n. And that concludes this presentation. I hope you enjoyed, and thank you for watching.